Hello, ladies and gentlemen. Today we're going to continue on our journey of simplifying radicals and exponents, and we're going to need that perfect roots table that we made, as well as your foldable, okay, your notes where we were taking them, and a calculator for sure. Okay, so make sure that you have those things handy as you're kind of working through these things with me. So this is what our foldable looks like. We've already done this part right here, simplifying with exponents. Today our focus is going to be simplifying those roots. So we're going to be working on that page. You're going to want to open up your foldable and take your notes there today. So when you open up your foldable, this is what it's going to look like. You'll have the top flap and the bottom flap. Here's the fold, okay, right here. So on the top flap up there, please make sure that you write that heading or these big ideas where they go in your foldable to kind of keep things organized. On the top, we need to write know your perfect roots. This is the key. That perfect root table is going to be important to us. We're going to do some examples without variables, without letters, and then we're going to do some with variables. And we're going to do 4 of each. So if you wanted to, you could divide it into 4 regions. You could number. We're going to look at 4 examples without variables and 4 examples with variables. Okay, today, very nice. Get those numbered, and here we go. You need this beautiful table. I will refer to it often, so please make sure that you're ready and you have that with you because we are going to need to find some perfect roots. So here are our first 2 examples under simplifying without variables. So number 1 and number 2 on the top. We have the square root of 40, and then the second one there is the cube root of 40. So let's first start with the square root of 40. Here's our number 1. So if I was going to simplify the square root of 40, we've done this already this year. Remember, the idea of simplifying radicals comes from understanding perfect roots. This is a square root. So when we break apart the square root of 40, we want to break them apart into something times something, but one of those has to be a perfect square. So what is a big perfect square or any perfect square that divides into 40 evenly? The answer is 4. Okay, 4 times 10 makes 40, and 4 is a perfect square. So when I simplify the square root of 4, I get a 2. When I simplify the square root of 10, that stays. And here we go, final simplified answer for the square root of 40. You worked on those in geometry. You also did them again earlier this year, but now it's time to go to other types of roots. Notice on example 2, the index is now a 3. That means this is a cube root. We simplify using the same process. I break it apart, but not into square roots, little cube roots. And with that in mind, I don't want to use my perfect square list to break him apart. These numbers are not helpful to me. Okay, what's now helpful to me are these numbers because I'm talking about a cube root. These are for square roots. Cube roots are the ones I'm going to use. So which of those perfect cubes divides into 40? The answer is 8. So if I look now and I simplify 40, I'm going to break them apart into 8 times something, 8 times 5. I chose 8 because 8 is a perfect cube. The cube root of 8 is a 2, and the cube root of 5 I will just leave. So the answer is 2 cube roots of 5. Okay, let's look at 3 and 4 here that go in your foldable. What about the cube root of 72? Same idea, we're going to break them apart, but we're going to use numbers from that cube root column or that cube column in your table. So we're still right here. Which of those numbers can divide out of 80? Or not 80. What did I say? 72. Yeah, 72. Which of those numbers can divide out of 72? 8. We'll do it again. 8 times 9 sounds good. Cube root of 8 is 2. Cube root of 9 is, don't know, we'll leave them alone. So 2 cube roots of 9. Done. What about the 4th root of 512? So now, again, we're breaking them apart, but we're going to use a different list of numbers. Numbers that are 4th root Okay, they're perfect fourth roots. So if I go back to my chart, now we're looking over here in this column. Which of those numbers can divide out a 512? The answer is 256 does. 256 times 2. Okay, fourth root of 256 is just the number 4. It is a perfect fourth root. And then fourth roots of 2 is my final answer. 4 fourth roots of 2. Okay, so those are some where we don't have variables. Now we're going to put some variables on the inside. So we have numbers and letters. Here's where things get a little sketchy. Okay, be careful, pay close attention. So 1 and 2, 3 and 4, here we go. First thing, or my first suggestion would be to think about these as two separate problems. Let's just deal with the number first, okay? I have a fourth root of 625. And then I have a fourth root of the x stuff, okay? The x to the fourth. What is the fourth root of 625? Well, let's look in our roots table. And that actually has a nice value. The fourth root of 625 is 5. The fourth root of x to the fourth. If you remember this idea about roots and powers canceling, the fourth root will cancel out a fourth power just like a square root will cancel out a squared. So that's kind of nice because all of this gets canceled and you're just left with an x. So my final answer is 5x. Okay, let's look at that second example. Let's also think about this one in the same way. I have a cube root of 64. I have a cube root of some y's. Okay, what about the cube root of 64? Well, that's just a 4. But this cube root of y to the sixth. See, the sixth power and the sixth index, or the third index here, or the cube root, does not cancel out. But if I had an index of 3 here, could I rewrite these 6 little y's in a strategic way that would allow me to cancel things? See, y to the sixth is the same thing as y to the third times another y to the third. That'd be 6 little y's, right? If we were to expand them all out. And so with that in mind, if I put a cube root sign over both of those separately now and don't look at them together as 6 little y's, but look at them as 3 and 3, now they do cancel out and I have a y when I cancel and a when I cancel. Look at that. I'd have a y and a y times a y makes a y squared. So my final answer is 4y squared. Okay, 4y squared is what that works out to be when he's all simplified. Okay, let's keep going. Let's do 3 and 4 here, see if we can continue to make sense of this. So let's do the numbers and the letters. Don't worry, yes, there's an A and a B in there. Don't worry, we're going to do them separately. Here we go. What about the fifth root of just the 4? Is there anything we can do with that? No. So fifth root of a 4 is just going to be a part of my final answer. Let's do the A's. Fifth root of a to the 10th. Now, a fifth root and a 10th power do not cancel out, but can I think about those 10 little a's in a strategic way that would allow me to cancel some? Yeah, 10 little a's here would be like a to the 5th times a to the 5th. That'd be the same thing as a to the 10th. And now if I wrote that little symbol over each of them, I could see now that the fifth root and the 5th power will cancel out, and I'll be left with an a and another a here. So that'd be 2 little a's being multiplied by each other. That'd be an a squared. Now those a squareds are not inside any root signs, so I'm going to write them in the front of my little radical part of my answer down here. So I've done the a's now. Now let's look at those b's. I have a fifth root of b to the 6th. Again, a fifth root and a 6th power will not cancel out. But I need to think about those 6 little b's in a strategic way that would allow me to cancel. So what if I had the fifth root of b to the 5th? I'd use up 5 of those b's, but I'd still have one little guy left over in there. B to the 5th times another b, still b to the 6th, but I rewrote it in a way where one little b right there would come out, and that other one would have to stay in. So my a's and my b's look like this. So far, I have these things all on the outside, so an a squared and a b. I'm just going to rewrite my answer over here. A squared and a b on the outside. And then on the inside of that little fifth root sign, I still have the 4 that we couldn't do anything with from over here, and the leftover b right here. So here's my final simplified answer for number 3 right there. Okay, so number 4, I'm going to do a little bit faster without showing all the steps there so you can kind of get a feel for my thinking. I showed them all to show you what I was thinking about when I was doing them, and now I'm going to show you again how to think about it but not necessarily write them all out. Let's look at just the number here, square root of 40. Didn't we already simplify that one? Yes. We said that was 2 square roots of 10 if we remember right. So this becomes 2 square roots of 10. 2 on the outside of the radical sign, 10 is the radicand inside. Now let's look at the x's. Remember, this is a square root. It's like there's a little 2 right there that we never write. So when you think about this, remembering what I'm going to do, I'm going to think about these 5 little x's in a strategic way. Basically, I'm making them into groups of 2 so that they can cancel with this x squared. So here's the quick question I ask in my head. I say, how many groups of 2 can I get out of x to the 5th? The answer is 2 of them. So I'd have x and x that are on the outside. How many would be left over on the inside? That's right, just 1. So I'd have 1 left over on the inside. Because if I take 2 groups of 2 out, that's like taking 4 little x's out, essentially. Okay, there we go. These are the things that are on the outside and on the inside. So my final answer is 2x squared. And I'd have a square root of 10 inside and an x inside. Boop, there's my final answer. Okay, so with that in mind, that is what we're going to be doing. Taking a look at simplifying those square roots when they have numbers and variables on the inside. It takes some practice, but you will get it, I promise, okay? See ya, and thank you for taking some good notes.